the SolidWorks, making the pins, and then you just dimension it, and then you start drawing these lines, and then you can put in a arctangent, and then you can start getting dimensions for that, and then you can mirror this across to this side, and then you start extruding. So it goes through everything, what buttons you need to hit, extrude, whatever, put in the thickness, mid-plane, and then you can put pockets into it. So it tells you, oh, just put a pocket like that, and then you can mirror the pocket to the other side like that, and then you can put fillets and fillet more, and then, yeah, essentially fillet. So you can get something like this as your end connecting rod, probably.
Mm-hmm.
I didn't fillet extensively because when you go to Abacus, the problem is if you fillet a lot, then you have to have very small mesh. It's a student version of Abacus, so you're only limited to a small amount of element size. So you got to be careful with that. So, but you can still get a pretty good model of it, So, this I think was just getting the mass property, or you can put in. So you can go to the material property in SolidWorks, and you can say you can pick a material with your same density, and then you can do mass properties and find the inertia and everything like that of the real connecting rod you have. And then you can go through, and now this is the finite element analysis in Abacus. So if you want me to go through this, I can show some of this on the screen.
Great.
Okay, let me just close this out. And then, oh, that was the Abacus. Isn't that full screen? Okay. Okay, so to start it up, you just go like this, Abacus CA.
This is the student version of Abacus?
Yes, this is the student version. This is the same one that 168, Finite Element Analysis, they have a license for it. So I'm sure you can ask for the same.
This, yeah, I'm going to ask for it actually this week.
So you just open it up, and the way, so let's go File, Open, and I'm just going to open up an already done project of this. So in this thing, at the end we had this final connecting rod, right? Looked like this, and I could open it up in SolidWorks, and and then in Abacus, what I do is I import this part straight into here. So to do that, you can. That's the first thing you want to do is you want to open this up, and then you want to change your workspace to your correct workspace. And then you can go to the model and you can rename it. And then you go here and you say import. So if I go back to Abacus, I just go File, Import, and you can import a part. And that's what you're going to want to do. So you import a part, and then you go through and you select the file. You select the file that you saved as a parasolid. Because, in the other thing, at the very end, I had them export the model as a parasolid. Yeah, export it as a parasolid, as you can see here. And then you can import in Abacus the model as a parasolid. And it's a pretty good model, It doesn't lose a lot of quality or anything. So there you go, you have the model. So that's your first part. So the way Abacus works is you have your parts, your properties, assemblies. These are just modules on how you set up the whole finite element procedure. But you can access everything by just right-clicking on things. So I can create a part. I can go create and then add this in. And then, so in these parts, I have 3 parts. So this is the first part. This is the connecting rod. And I imported that. Then I created another part, which is this crankshaft. Now I just double-clicked on it. See, I accessed it. Now this is the crankshaft pin. I drew this pin in Abacus. So in this model, it goes through and it shows how you do this. So you go create, and you just draw it in Abacus, and you just follow add dimensions. I mean, it pretty much is pretty self-explanatory. You add depth to it. Then you go to the material properties. So material, I can create a material, and I can go mechanical, elastic. I can put in the Young's modulus, the Poisson's ratio, all that. And then I already had created material, see, forged, And then what you need to do is there's all these subtleties, but see now I just because I right clicked and I created, I changed the property. So this is the other way to get to things. So like if I go part, I can create a part doing the same thing. So in Abacus there's multiple ways to do the same.
Do the same function.
Yeah.
Mhm.
So I did the whole tutorial from this because I thought it was easier for people to see and access it just by right clicking, kind of like console. But you can do the same. All the buttons are here for the same procedure. So in the properties, you're adding material properties. In the assembly process, you're essentially putting the. See, now I put all the parts in one assembly, and then I mated them and I did all that. So if you go back,
So you did mate the parts,
yeah,
the
you have
pairs.
to mate the assembly together.
Yeah, you have the explanation for that, right?
Yeah, it's all in here. So you can, you have to assign sections and everything to the model. So this is, so I imported this, the connecting rod and this pin, and then what I'm doing is I have to go through some steps to say that, oh, I'm gonna put this in. This is where I put the contact pairs essentially on it. I create a contact interaction, and then I say that, oh, this is interaction between that and this object. And I say, oh, there's small sliding between the interactions. And then in the assembly, then I say stuff like, coaxial, so it'll make it go from here to here, and then I say, oh, face to face, and then it'll give it a certain distance. So then you can assemble
It's similar to SolidWorks.
Yeah, you're essentially, fixing it together, assembling.
Right.
So that's pretty much, and then I had to add springs. So there's
So you have springs between the pin and the connecting rod?
You have to put small springs because your degrees of freedom. You don't want the connecting rod to just go out of plane.
Yeah.
So because initially when it's in contact, the contact pairs, they solve by essentially making small displacements and then and just to initiate contact, and then they say then you want to put a step where it adds the loads to it once the objects are in contact, because Abacus has issues where it doesn't realize it's in contact and then it will fall out of contact. So there's also steps in Abacus, and it's like essentially saying the first step is make sure they get into contact, and then the second step is now apply loads, and so it will build and solve, making sure that the steps are complete. So yeah, so I mean,
But do you have to play with the stiffness of the springs in between the?
Yeah, I just made them one, so they're really light springs, just to make it so the degrees of freedom are there, so it doesn't rotate. But then once it's in contact, it has no effect on it.
Okay. So you eliminate rigid body motion, basically.
Yeah, it's just essentially tricks to make the solver work properly.
Yeah, right.
But you're not the physics is not being modified. I think that's, yes, these were just adding springs, and it just tells you exactly what to do. You just put in the degrees of freedom that are allowed to rotate and move. So, and this is just now you're putting boundary conditions. So we can go back to Abacus and I can show you some of the stuff that goes on. No, this thing. Okay. So yeah, again, the assembly. This is the inner. Everything is an instance. So that whole thing is an instance. That is an instance. So you right click and you add an instance to the assembly, and then you just made them. So you can see what I did with them in this features, or no, wait. Constraints. See, I put a coaxial constraint. So you can delete anything that you want. So if I make a part, I can go here and I can just delete this coax. You know what I'm saying? So these are the steps. So my initial step, which is essentially I put boundary conditions. I put an interaction. I put the contact interaction. I put the boundary conditions that this is fixed. So here, if I edit this, here, the setup contact. That's where I do this. So here are my two boundary conditions. I'm just going to edit this to show you. See, this is I set this to be a. So this whole thing is fixed. In these are all the directions of display, translation, rotation. I'm saying the whole thing is pinned is fixed, and then this pin is let's see it. This pin over here is fixed in the U direction. It can't go up. It can't go this way. It can't go out into the third dimension. But it can slide. It's like the prescribed displacement.
Good.
and then this is where I applied loads.
Mhm.
And you can access these by just going to this. These have all my loads, so my axial load. So like I can edit my axial load. You can see this is all my axial load. So the way because the axial load is like a number, I put in oh, this is the body load. Yeah, this is the body load. It's an analytical field. So I can explain what I'm doing with that.
So the load, you import the file for the body load?
So
or?
that's the kind of the body load was kind of hard, but what you do for that is you essentially here you go. You run this M file, and what it does, just like COMSOL, I put all the equations in COMSOL, so when the angle changes, it recalculates everything. Well, instead of putting all that data into Abacus and have it built in, I wasn't sure how to put all these parameters and stuff.
Yeah.
So I just made an M file that would do the calculations. So if you want because the whole point of this design is that you don't want to do a parametric sweep because it's a giant finite element model. It takes 20 minutes to run one crank angle.
Yeah.
So the whole point is not to do a parametric sweep of all the angles. So you probably, most likely, you're going to have like the highest angle that gives the highest critical load.
Mm-hmm.
I mean, for mine it was like 16 degrees. You know,
Yeah.
like there's going to be one or the highest tension load. You know, there's going to be a couple degrees that you're going to check. So all you do is you run this M file, and it will give you this data, and you just put in the crank angle that you want to check for, and it will give you this data. And then you just take this data and you write the body load equations like this manually. So you can see that here, if I zoom in on this, in the screen where I had this expression field, I just wrote this equation in manually. And the only variables is x and y, the positions of your global coordinate. So
the output from that would be the body load at each node.
Yeah, exactly. So this will calculate the body load at each node. That's why if you look at this, all of these have different like lengths because they're different sizes. So some of them are larger than
So this is the imported file basically. Yeah. The body load of the imported file.
No, you don't import the file. I mean, you run the MATLAB file.
Yeah.
You grab the numbers manually, and you just go and I go to my analytic because here there's if I were to create a load, right?
Yeah.
I create a load. I say it's a contact or something. And then I select. Oh, I'm going to select this surface. Oh, sorry. I have to select a point. Wait, let me just forget that. Create. I wanna create like a pressure load or here body force.
Body force.
Okay, let's create a body force. So I'm going to select that body and say okay. Then what you do is you get this screen, and you do is you hit this function for an analytical field. So now you're creating an analytical field, an expression field. So I create an expression field, and so this is where you type in your expression. So there's x and y coordinates of your global
function
coordinates.
of x.
So you just manually write in this like 5 times
x plus x squared and so on.
Yeah, exactly. You just type that in. You say okay. And now that's fields, and then you just access it and say, oh, I want this analytical field that I just created. And it uses that. And then you put in 1 because it's what component direction is that analytical field saying?
Right.
Oh, if I want to be, component 1 is in the x direction, component 2 is the y direction, z is the, So, and I just say magnitude of 1 because the analytical field calculates the actual value. And then you can amplify it by saying 2, like it would be 2 times. But so yeah, that's how you create the body load. So you do that for the...
and that analytical field is coming from COMSOL?
No, so you run this... this M file.
The M file will
so this
fit
body
the
load,
data?
I give them the expression. So this is the expression.
Yeah.
And all they have to do is they ran this data, right? So D gamma and DD gamma and rho, and they literally just grab those numbers and they write it in this form.
Oh, okay.
See
so
X and
this
Y.
is so the body loads from the equations of
Exactly.
the dynamics. Yeah. Okay.
Yep. So that's the that's like all the loading, really, the conditions, and the same for the axial load. But you don't have to do an equation for that. It's just a fixed number, but they still grab it out of the.
Yeah.
So what is left? So you set up the whole model with the loading conditions and your boundary conditions and the interactions, the interaction properties, like had a contact property. That's just, I'm setting up a normal contact property, and you just, if you follow the tutorial, it sets up everything. Yeah, and then you have to make sure there's small sliding interactions and stuff. So the final thing you do is once this is all set up, and you've essentially gone through everything, loading, and the mesh. So then you have to mesh these elements. So like this is the mesh I used. You can get finer, but if you get too fine, you don't have enough elements. I think it's maxed at like 100,000 or something like that, or 10,000. So you can't go extremely high. Obviously, there's ways to improve this. Like first of all, this analysis is symmetric, so technically you could just cut it in half and not have the other half. Like if you want to optimize this. And the other thing is that when you do the analysis, you can see that you're going to get high stress concentrations at the contact, right? At this area. But like the mesh size is very, very large. So you can partition this, and you can make it a lot more complicated.
Right.
But I thought like for now, this is the very last thing. At this point, they're going to be like, wow, this project's already like very time consuming.
Exactly.
So,
Yeah. This is when they go out and work and actually make money. Then
then
that'll be
you can
the job.
partition and really do an advanced.
They get paid for a couple of weeks to do this job.
Yeah. So yeah, there's a lot more things you can do with this. And I just picked TET meshes and stuff like that, but you can go in. So finally, you do the mesh, and then you go to the job, and you create a job. You just go right-click and create a job, and then you can run the job. Just go run and submit the job, and the job is just taking all this data and saying, now I'm going to go to the solver, and I'm going to solve it. So once it's done, you can go to the visualization module. So you just go like this. And I'm going to open up a job I've already ran before. Let's just take it at the highest one, that's 16 degrees. So this is when the axial load is really, really high from the piston. So it comes in and it comes in, and then so you can hit this button and say plot deformed shape. And so you can see that's the deformed shape now, because it's been squished a little. And then I can look at the stress plot of this. So it automatically gives you von Mises, but you can change this to whatever you want. So you can see this is S for stress and von Mises, but I can print the S11s. I can do the max principal. I can also do the deflection. So you can do whatever you want. And then, so you can see that I have, high stress concentrations right here. You know what I'm saying? So you can make that mesh high or whatever.
Right.
So that's essentially how it works. And then like if you want, you can see a one where it's in bending. That's 32 degrees for mine, negative 32. So in the tutorial, it shows you how to do all this, where you can go to the see. So like you can see all this, and it turns on, and you can turn the perspective off, and then here. So this is this model, and I'll show you what it looks like. So that's the deformed. So you can see the contact stress areas and everything.
It's beautiful.
And then this is you can go, and I think you can even set it so you can see plot. You can allow multiple plot states, and then you can plot the undeformed shape. So you can see how much it deformed. Obviously, you can set the well, we haven't figured it out, but there's a way to set. See down here, you have a deformation scale factor. So there's obviously a way to reset the factor. But the cool thing is now you can go and you can check your 2D model and see like, oh, it actually moved in a little and it bent at negative 32. And you can go and check your console. Make sure the console matches your 3D model, because if it doesn't, you've got problems.
Yeah.
So,
very good.
Yeah.
Excellent.
Very nice.
Yeah.
And then you can output the stress data again, like as a whole, so you can have all the nodes, you can output all the stress data if you want to
To
manipulate
do
it.
for post-processing.
Yeah, if you want to do some crazy I mean, you could write a fatigue code. I mean, the fatigue code technically you could write it so that you get the third principal direction, and you can do, you know, I mean, there's a lot of crazy things, and you can also do really cool things where you can cut through the planes to see, like the geometry. So I'm just cutting through different parts of the connecting rod where the highest stress is. And you can see things that you normally wouldn't see, like, you know, the distribution and everything.
Yeah. Okay. Great.
Yeah. So
Very
that's
nice.
pretty much it.
Very nice. Excellent. Thank you so
Amazing
much.
amount of work you put in.
Yeah.
It's
So
very well organized.
how long did it take you to develop all of this, Dan?
I don't know. The rainflow is the hardest thing. I'm counting that. Yes. It's difficult.
Yeah, you did a great job. Thank you so
Can I
much.
have a copy of it?
Yeah.
Yeah, I brought my